Welcome, my name is Martin Springer and I'm going to present on the materials characterization, accelerated testing and constitutive modeling of electrically conductive adhesives. This work is motivated by the emergence of electrically conductive adhesives as interconnect material in new embodiments of PV modules. This can be either in ribbon bonding, where ECA can replace traditional metallic solders, or in shingled cell designs, where ECA is establishing the interconnection between cut cells. In general, ECAs are composite materials consisting of conductive particles and a polymer matrix that holds the particle in place and establishes adhesion with the adjacent materials. The change from traditional metallic solders to ECAs represents a significant material change, but the reliability and durability of ECA modules is still assessed by accelerated tests developed for solders. Those tests might not be appropriate for the new interconnect type and may not be representative for the long-term performance of ECA modules. Therefore, within this project, we are working on developing a sound physical understanding of ECAs and their degradation mechanisms to better predict the long-term performance of PV modules using ECA interconnects. Let's consider solder as an example. In order to predict the long-term performance of solder, the material behavior had to be characterized, constitutive models had to be formulated, and damage metrics needed to be identified. With this information, it was possible to conduct predictive simulations with the help of the finite element method to simulate the accumulated damage in solder joints over the course of 1 year at different locations around the world. In the remainder of this presentation, I'm presenting our efforts in recreating this process for electrically conductive adhesives. We started with the characterization of the viscoelastic material behavior of ECAs. We can do this in either the time or frequency domain and need to take into consideration the rate and temperature dependence of the material. We use dynamic mechanical thermal analysis to characterize the storage and loss modulus of the material within a relevant range for PV applications. We define the temperature range from -40 to 85 C as sufficient for the material's characterization and found that the relevant rate dependence ranges from slow time periods in the order of 1 year, representing seasonal effects, down to milliseconds, representing vibrations from excitations due to wind loading. With this characterization, we were able to use a generalized Maxwell model to describe the constitutive behavior sufficiently well. As can be seen on the right-hand side, a single Young's modulus value would be insufficient to describe the mechanical behavior. Instead, a long set of Brownian terms and a time-temperature shift function are required to fully describe the viscoelastic behavior of the material. We've characterized a set of different ECAs, all marketed for the PV industry. Here I've plotted the storage modulus values for 4 ECAs with the relevant loading rates and temperature ranges occurring in PV modules. To exemplify the difference in mechanical behavior between ECAs, let's consider a shingled cell module as depicted on the right-hand side, and assume that the ECA joints have a uniform temperature of 35 C. For the epoxy-based ECA number 1, the storage modulus curve at 35 C is indicated with a red dotted line, and is higher than, for example, epoxy ECA 3, where the storage modulus curve at 35 C is indicated with a green dotted line. This difference in the storage modulus between the two ECAs leads to differences in the stresses and strains inside the ECA joints as illustrated on the right-hand side. The higher storage modulus of epoxy 1 leads to higher mechanical stresses inside the ECA joint, but lower deformations and therefore strains. On the other hand, the lower storage modulus of epoxy 3 allows for greater deformation and therefore higher strains, but lower stresses. Further details on this work can be found in our paper. After characterizing the viscoelastic material response, we worked on identifying possible damage mechanisms and metrics. Therefore, we created a thermal cycling test vehicle and subjected it to accelerated testing conditions. We used ECA to glue copper cylinders onto a direct bond copper substrate. The copper cylinder and the DBC board have greatly different coefficients of thermal expansion, leading to high stresses and strains at the ECA interface during thermal cycling. We monitored the interface area with acoustic microscopy and detected mechanical degradation in the form of interface area reduction. In addition, we monitored the electrical conductivity and found that with decreasing interface area, the electrical resistance increased. After 1200 thermal cycles, we cross-sectioned the individual copper cylinders and found two different failure modes: adhesive failure between the ECA interface and the adjacent copper material, and cohesive failure within the ECA. Both failure modes can be described with fracture mechanic approaches, either due to interface failure or cracking. Hence, we've decided to pursue a characterization of the fracture mechanics parameters of ECAs. We can differentiate between three crack growth regions. No crack growth. Here, the deep bond driving forces are too small to cause any crack initiation or propagation. Critical crack growth. Here, the deep bond driving forces are high enough to cause crack initiation and propagation, and possibly ultimate failure of the ECA joint. In between, we have a region of subcritical crack growth, which can be caused by a variety of different mechanisms, as for example, environmental assisted cracking or the material behavior itself, like viscoelasticity. Since we expect our modules to be in the field for a long time, we certainly don't want to have deep bond driving forces within the critical nor subcritical regime. One straightforward technique to characterize the deep bond energy is the single cantilever beam method, as depicted here on the right-hand side. We picked an epoxy-based ECA and conducted a series of tests under different environmental conditions. A subset of our results is depicted on this slide. For further details, please have a look at our paper. The left-hand plot shows crack growth curves or subcritical crack growth under different temperatures in a dry environment. We can see that with higher temperatures, the deep bond driving forces required to cause crack propagation are decreasing, meaning that it is easier to propagate a crack at higher temperatures. The shape of the curves characterizes a slow viscoelastic creep crack growth mechanism, which can be seen by comparing the measured curves with the stylized image on the right-hand side. Next, we will take a look at different moisture contents inside the ECA. We can see that the shape of the curve is different between measurements in a relatively dry environment and measurements in a humid environment. At high moisture levels, the subcritical crack growth mechanism is changing from a slow viscoelastic creep crack growth mechanism towards an environmentally assisted subcritical debonding mechanism, which is evident by the almost horizontal part of the curves that represents the transport control region. Also, the failure mode is changing from a cohesive failure in dry environment to an adhesive failure in humid environments. These results confirm that cracking of epoxy-based ECAs is more likely to occur when high moisture contents are present. Now we are switching gears towards predictive simulation. In collaboration with Sandia National Laboratories, we developed a multi-scale modeling approach that propagates the required information from a full-size 3D model to a 2D 5-cell fracture mechanics model. The full model is subjected to accelerated thermal cycling conditions, and the resulting deflection figure is used to compute the deep bond driving force at the ECA joint with the 2D submodel. A corresponding research article got accepted by the Journal of Photovoltaics and should be available online soon. This multi-scale modeling approach allowed us to investigate the deep bond driving forces during accelerated thermal cycling for 6 different initial crack locations. We placed those initial cracks on the left and right-hand side of the ECA joint and at the top, middle and bottom location. The top and bottom location represents adhesive interface failure, whereas the middle location presents cohesive failure. The center figure shows the deep bond driving force derived from the multi-scale modeling approach, which follows an inverse relationship to the applied temperature profile. We found that an initial crack at the middle right location delivers the highest deep bond driving force, meaning that an initial flaw at this location in the ECA joint is most likely to initiate a crack. We further found that typical submodel boundary condition assumption, as a flat glass front surface depicted on the left or a completely free submodel depicted on the right, tightly bound our results from the multi-scale modeling approach, which allows us to bypass the added complexity of the multi-scale modeling approach for similar type simulations while obtaining relevant results. Finally, we expanded our 2D submodel to simulate 3 different types of on-sun exposures. a sunny summer day, a cloudy summer day, and a cold winter day in Golden, Colorado. The temperature profiles are depicted in the left-hand plot. The resulting deep-bound driving forces are presented in the top center plot and follow an inverse trend to the temperatures. Hence, the cold winter day represents the harshest conditions for the ECA joint with the highest deep-bound driving forces. Further, we also investigated the impact of the joint quality by varying the initial crack length. A longer length presents a bigger flaw, which is an indication for a poor joint quality or otherwise damaged joint. Now we can compare our deep-bound driving forces from the simulation with the measured subcritical crack growth curves derived earlier. I've indicated the cold winter day driving force with a blue dashed line, which is around 100 joules per square meter. We can see that for all investigated temperatures and humidity levels, the driving force is too low to cause subcritical crack growth. Similarly, for accelerated thermal cycling, the deep-bound driving force of 150 is still below the threshold value. If we look at the joint quality, we see that initial flaws would need to be bigger as at least half of the ECA joint width to cause subcritical crack growth. We've discussed the mechanical and fracture behavior of ECA joints. However, this does not answer the question of how the electrical performance of a PV module is affected. To answer this question, we need a unified constitutive model that considers both mechanical and electrical properties. In order to measure the electrical conductivity in dependence on the mechanical loading of the ECA, we had to establish a new measurement setup. The microstructure of ECAs is depicted on the left-hand side, where it is easy to see that the electrically conductive particles are held together by a polymer matrix. Mechanical loading, for example, is indicated here tensile loading, will stretch the polymer matrix and individual particles might lose contact, which may then result in an increased electrical resistance. To test this hypothesis, we have created a uniaxial tensile loading configuration with simultaneous electrical resistance monitoring. We use ECA bulk specimens, which are gamped via tensile grips that are electrically conductive, and use a 4-wire resistance measurement to sense any resistance changes inside the ECA. The grips are electrically decoupled from the remaining load frame. Below the sample, a load cell is mounted, and above a linear actuator is connected to apply uniaxial displacement. The new load frame is placed inside an environmental chamber to control temperature and humidity. If you're interested in this new capability, I encourage you to check out our poster presentation where we provide more details and preliminary results about this effort. Here, I'm just going to show a quick overview of 3 preliminary measurements that we've conducted with the new setup: a relaxation measurement, a tensile test until rupture, and a thermal measurement. The upper row indicates the mechanical strain and the lower row the mechanical stress. In the case of the relaxation experiment, the ECA was loaded up to 10 megapascals. Afterwards, the displacement was fixed, meaning the strain was kept constant and the sample was left to relax, resulting in a decreasing mechanical stress, which also led to a decrease in the electrical resistance during relaxation, indicating that there is a correlation between the mechanical stress and the electrical resistance. In the case of the rupture test, the sample was loaded until the ECA specimen fractured. A steady increase in stress, strain, and resistance can be observed until rupture occurs. At this point, the load drops and the electrical contact opens. The right-hand plots show a thermal measurement from -20 to 60 C. A constant stress of roughly 0.4 megapascals was applied via load control. The used epoxy-based ECA has a gas transition temperature of around 50 C, which explains the difference in slopes of thermal strains and electrical resistance, which is affected by the thermal elongation of the sample. Those early results indicate the importance of taking the temperature and time dependence of the viscoelastic material response into account when characterizing the electrical conductivity of ECA. In summary, we have finished our efforts for the mechanical and fracture characterization of ECAs and are continuing to quantify the electrical properties. Further, we've developed a predictive simulation capability using a multi-scale modeling approach, allowing us to conduct a fracture mechanics assessment of the ECA joints. In the next step, we are going to include electrical properties into our simulations to allow for the prediction of the module electrical performance. Thank you for listening, and please feel free to reach out to me if you have any questions or comments regarding our work.